Let's get started. So we are very happy to have our own Rebecca Deason today to give us the seminar. She did her bachelor's at Northwestern, and then she was a PhD student at U Chicago. She worked with Damiano Caprioli and Angela Olinto at Chicago. And today she'll be talking about some of her interests on unveiling particle acceleration and the non-thermal universe, which apparently was also her thesis topic.
Yes.
Please take it away.
Yeah. Great. So thank you for that introduction. Thank you for being here today. Today I'm going to be talking about how we can better understand particle acceleration and what a proper understanding of the microphysics of particle acceleration can teach us about extreme astrophysical phenomena. So I'm particularly interested in the things that launch outflows and therefore shocks. Those shocks can go on to accelerate particles, and those particles then produce observable non-thermal emission. And so by actually understanding the microphysics of that particle acceleration, we can learn more about how these objects evolve and the environments into which they expand. But before I get into these objects, I want to take a step back and say that at the core of what I do study cosmic rays. And so these are charged, typically mostly protons, energetic particles of extrasolar origin. And although we've been studying them for more than 100 years at this point, we still don't have a complete picture of where they come from or how they're accelerated. The current state of the field, we have this beautiful spectrum that spans more than 10 orders of magnitude in energy for all these different types of particles, and it follows roughly a power law over that range. But understanding what all these little features mean, things like you've got this knee and you've got the ankle, understanding their origins is still an active topic of research. And so in particular, when you try to get at that first question, where do they come from? The state of the field basically divides the cosmic ray population into two categories. So at the lower energies, up to roughly a peta-electron volt or 10 to the 15 electron volts, we believe these are of galactic origin, likely accelerated by supernova remnants. And you can make a nice little argument where if you take 10% of the energy available to you from supernovae and you convert it to cosmic rays, you can fully reproduce this flux that we see. At the higher energies, we know that these are of extragalactic origin. There's a dipole anisotropy that we have observed, and it doesn't point toward our galaxy. However, what is actually accelerating these particles, we don't know. There are lots of theories that invoke some portion of AGN, likely AGN jets. You can also play games with Star Wars galaxies. But the truth is we don't know where these extragalactic cosmic rays are coming from. But for most of this talk, I'm actually going to focus on these better understood particles, the galactic cosmic rays, where we think we have this theory for how supernova remnants are able to accelerate cosmic rays. So not only can you make this energetics argument that says convert 10% of the energy to cosmic rays, you can reproduce the flux, but we also have a theory for how the forward shock of a supernova remnant is able to accelerate particles quite efficiently. I'll spend a lot of time talking about that shock acceleration paradigm. And so in that case, if we believe that shocks are accelerating particles and we have a theory for what kind of particle distribution you should get, now we can actually take that question and flip it on its head and say, if we know how these are being accelerated, what can we learn about their accelerators? Yeah.
Just a quick question. The two curves that don't lie on top of each other, is this some systematic, like the PP, I guess it's Auger is the bigger one?
Oh yeah, so this, down here, yeah. So so these two are within error bars. These are actually, I think this has got a little cut off, but I think these are different particles actually. So this is the proton spectrum, which is in pretty good agreement. Here you can see it a little more clearly. So this, I think this the label didn't cut off. Oh, sorry. Okay, so are you talking about these guys right here?
No,
or
just below the knee. Below the knee.
Below the knee.
Just
yeah.
PP and then the other one.
Yeah, so I think it's some sort of systematic. So there are kind of some sets of experiments that have like a very systematic offset that are completely outside of error bars, and I'm pretty sure. The thing that's a little bit dangerous is there's also an energy calibration component to all of this when you're trying, and so I think that's my opinion, but it's very easy to get this in this kinds of experiments. Yeah, so that brings me to the outline of this talk, which is answering those two questions, which is how are galactic cosmic rays accelerated and what can we learn about galactic cosmic ray accelerators? So I'll start by kind of going over the standard paradigm, which is the shock acceleration and what kind of spectra you get out of it. And then I'll introduce some of the issues with that standard paradigm. There are places where it doesn't seem to agree with observations. If we go into the microphysics of particle acceleration, we might be able to actually resolve some of those tensions between theory and observation. And then I will again go to the second question and talk about what we can learn about galactic cosmic ray accelerators. So if we believe these resolutions of the standard paradigm, we believe we have a framework for how these are accelerated, what can we learn about the environments and evolution of things like supernova remnants, but you could also apply this to novae or AGN winds. There are a lot of different contexts in which this applies. I'll also talk about how cosmic rays themselves can affect the evolution of shocks, particularly supernova remnants near the ends of their lives. And finally, I'll talk about a question that is pretty hot in the field, which is what is the maximum energy you can get out of an astrophysical shock, in particular because there's a lot of tension that seems to say that you can't actually, that kind of tip of the galactic cosmic rays, supernova remnants can't quite get there. There's some tension there as well. But yeah, feel free to interrupt throughout this. If I don't get through all of these latter ones, I'm happy to save some of this for astrophysics. All right. So first of all, the standard paradigm, which is shock acceleration. So the picture to have in your head here is that protons and electrons can be accelerated at the forward shocks of supernova remnants via a process called diffusive shock acceleration, or DSA. And so just to orient ourselves, here we have a shock represented by tetra supernova remnant, and everything I'm doing is in the frame of the shock. So imagine that you are riding this purple shock from outward. From your point of view, you are going to see a flow in the upstream moving toward you at some velocity u1. That flow is then going to be compressed, heated, and slowed down to velocity u2 behind the shock. And we can characterize a great deal of the shock hydrodynamics via the compression ratio. So just the density ratio, or force conservation of mass, the velocity ratio between the down and upstream. And you can show by just solving conservation equations across the shock that if you have a strong shock, so you're going substantially faster than the speed of sound, that compression ratio is universally equal. Now, particle acceleration comes into this when we consider, say, a charged particle like a proton, and that proton is being pitch angle scattered by magnetic perturbations in both the downstream and the upstream. And so you can think of it as behaving diffusively. It's going to isotropize with first the upstream and then the downstream, respectively. And so that means that every time this particle crosses the shock, it undergoes a frame change. Or from the particle's point of view, when it's in the upstream, it's going to see the downstream flow coming toward it at u1 minus u2. When it's in the downstream, it's going to see the upstream flow coming toward it at u1 minus u2. So that means you have a head-on collision every time you cross the shock, and therefore a net energy gain. So this is your efficient acceleration mechanism that we call diffusive shock acceleration or first-order Fermi acceleration. Now this is cool because this is actually a universal acceleration mechanism. So I have been mentioning this in the context of supernova remnants, but in principle, any astrophysical shock should be able to accelerate particles, at least to some extent. So I'll be talking about how we can apply this to things like novae. There are also extragalactic supernova remnants, these really young radio supernovae. This could be relevant on much larger scales, so galaxy cluster shocks and AGN lobes, and then also in heliospheric contexts, there are interplanetary shocks and our SPAD shock as well. The other cool thing is this is not only a universal mechanism for accelerating particles, but it predicts a universal spectrum of particles. So to zeroth order, you can say that the spectrum of particles that you should get in momentum is a power law that goes as, so p to the minus qp, where QP, that slope, is basically set by the balance between the energy you gain with each crossing, so that's something that goes as U1 minus U2, and the probability that you get advected away from the shock and you don't return for another cycle. And that's also related to the shock hydrodynamics. And so what that means is you can actually characterize this slope entirely in terms of the compression ratio. And so this gives you this universal prediction that if you have a strong shock, QP is equal to 4. For most of this, I'll be comparing to observations. So I'll talk about this in terms of energy spectra. You have relativistic particles. This converts to a power law of energy. So this Q, so energy spectrum, is going to be universally equal to 2. That's our prediction. Now, the reality is a little bit more complicated. We don't have a universal population of e to the minus 2 shocks that we observe. But the first thing you can think about is, why might this not be the case? Well, you have to do some non-linear corrections to this. So let's consider the fact that you have a shock and it's accelerating particles efficiently. Now you have a non-negligible pressure from your cosmic rays. And so that's going to create this region that we call the precursor in front of the shock, in the near upstream. And it's basically a region of enhanced cosmic ray density with respect to the background plasma. And so that's going to basically create three regions that you need to consider: the downstream, this near upstream with a slightly slower velocity, and then the far upstream, which is the completely unshocked, unperturbed ISM, or whatever your ambient medium is. Now, how does this affect particle acceleration? Let's say that you have a particle with relatively low energy. So it has a smaller diffusion length. It's only probing the region from the downstream to the near upstream. This particle is going to see a relatively small compression ratio because it's not seeing the full one from the downstream to the far upstream. And if you look at that relationship that we had earlier, if you probe a smaller compression ratio, you're going to have a spectrum that is steeper than e to the minus 2, so Q greater than 2. Conversely, if you have a lot of energy, you're going to probe the full region from the downstream to the far upstream. So that's going to give you a compression ratio that you probe that's actually larger than 4, due to the fact that you have that non-negligible cosmic ray pressure. And so that has an adiabatic index of 4/3 rather than 5/3, makes your fluid more compressible, raises your compression ratio. And so that means that for these high energy particles, you should have spectra that are flatter than e to the minus 2, Q of less than 2. Putting that together, nonlinear DSA predicts this kind of concave spectrum. So this is in momentum, where the transition point from steep to flat is basically set by the extent of your precursor, or equivalently, the lowest energy where you start to carry non-negligible pressure. And so that typically happens around a GeV. And so that means that we can say that for relativistic protons, we expect their spectra to be relatively flat. So Q to be less than 2. And this is where we start to run into problems, because if you look toward observations, they point in the opposite direction. So we have a number of observations that indicate that cosmic ray acceleration proceeds typically with spectra that are steeper than e to the minus 2. Evidence for this includes the gamma ray emission from galactic supernova remnants. So that is probing the proton spectrum, and that gives you slopes in the 2.2 to 2.6 range. We have radio emission from young extragalactic supernovae. These are also called radio supernovae. They have very steep spectra, e to the minus 3 or so. And finally, if you look at observations of the galactic cosmic ray population itself, as observed at Earth, that goes as roughly e to the minus 2.7, the spectrum that I showed you earlier. And given what we think we know about how cosmic rays propagate, this requires that the cosmic rays be injected, so accelerated, with a spectrum that goes as e to the minus 2.3 to 2.4. Yeah.
So why are the particles gaining energy from the shock again?
So that's that diffusive shock acceleration. So that's basically they're diffusing, and every time they happen to cross the shock, they undergo a frame change that's basically the equivalent of getting a head-on collision. And so it's just like they're basically getting hit like ping pong balls back and forth across the shock, but with no friction, so they gain energy with each crossing.
Is it because the velocity on the other side of the shock is less than this side?
Yeah, it's the velocity on the other side of the shock is moving. It's a head-on is moving toward the particle from the particle's point of view, where technically these are diffusive particles, but if you look at the population of particles, the fluid on the other side is moving toward you, and so you get a head-on collision, like getting hit with a tennis racket or a ping pong racket. And so you basically get hit every time you cross the shock, and you gain energy every time because of friction. All right. So yeah, we have this issue with steep spectra, and we need to figure out why. And so that brings me to this next part, which is where we're trying to resolve problems with the standard paradigm. And so the first thing that we can do is we can look towards simulations. So you can go ahead and do kinetic simulations, where you basically, these are kinetic hybrid simulations, which basically means you have particle protons, and then you treat your electrons as a neutralizing fluid. This allows you to run longer because it's less expensive than full particle in cell codes. And so if you run these simulations of a shock, let particle acceleration proceed in this manner, what you are naturally reproducing, this was a 2020 result, is spectra that are steeper than e to the minus 2. So this is in momentum, so p to the minus 4, equivalent to e to the minus 2 would be horizontal here. You can see these spectra at all time steps, they're substantially steeper, and they're certainly steeper than the nonlinear DSA prediction, which is that dashed line.
No.
The other thing that I will mention is at the same time as they are seeing steep spectra, they are actually seeing enhanced compression ratios. And if you remember the relationship I showed you earlier Larger compression ratio should give you flat spectra, but here we see the opposite. And so we actually have steep spectra at the same time as compression ratios that are larger than 4. And so before I tell you what's going on, I want to take a moment to mention the thing that is very important for this particle acceleration process, but which I've kind of swept under the rug until this point, and that is magnetic fields. So magnetic fields are, of course, the thing that are scattering these particles, but they are also responsible for confining the particles. It's important to note that the magnetic fields in something like a supernova remnant are not the magnetic fields you have in the ISM. They're very strongly amplified. And so we have observational evidence for this, for example. So these are all different supernova remnants. You see there these really nice, thin, purple X-ray emitting rims. The fact that they're so thin means that electrons are losing energy on very short length scales. And so that means that you have to have a very strong magnetic field to create those synchrotron losses. And if you infer the magnetic fields for supernova remnants like these, you get something of order hundreds of microgauss compared to the ISM field, which is a few microgauss at most. So we know that this is the case. We also know from theory, from simulations, that cosmic rays are actually able to amplify magnetic fields themselves. So there are a number of simulations out there that do this. There are a number of different ways to amplify the magnetic field. The ones that I think about most in my work is there is this resonant instability, which basically says if you have these particles that are gyrating, they're going to excite waves in the magnetic field of wavelength comparable to their alarm radius. And basically you can tangle the field a little bit that way, but that actually tends to be underdominant. That gives you a delta B over V, so basically the fluctuation size that's of order the background field. But there's also this thing called the non-resonant, or I'll just call it the Bell instability, maybe because the person who came up with it, which is the idea that if you are accelerating particles, you're going to have some of these particles escaping. And so you have a current. And if you have a current of particles leaving the shock, you're also going to have a return current to neutralize. And so that return current is actually going to cause the magnetic field to puff out. It's going to start to tangle it, and you actually create this instability in which you can have strongly amplified turbulent magnetic fields. This is expected to saturate not at delta B of B of order 1, but when the pressure that you have available to you in drifting cosmic rays, so basically the pressure in that current, is of order the magnetic pressure. So there's kind of an equipartition argument that you can make here.
Delta B over B then is much less than 1.
Much larger than 1. So delta B is the perturbation, right, that you make. So the idea is you can get a very, very strong amplification, so large delta B over B. Yeah.
These, the ones which produce magnetic fields are also the ones which get accelerated, or?
Yes, and that's where things get fun. So this is a very nonlinear problem, is essentially what I'm saying. So the cosmic rays that you're accelerating are exciting the magnetic field, which is in turn scattering them, which is in turn yes. So you have this cyclical problem, and that's actually something that comes into play with this thing called the post-cursor. So this is what we think is causing the C spectra. And so when you look at these simulations, we know that we are creating magnetic fluctuations in the upstream. So basically you have these cosmic rays that are streaming, they're escaping, they're causing this turbulent amplified magnetic field. And then the thing that we did not predict from theory, this is completely empirical in simulations, is that when these magnetic fluctuations are infected into downstream, they don't slow down as much as the background plasma does. So they're actually drifting with respect to the background plasma in the downstream. And empirically, they're drifting at the local Alfvén speed. I mean, broadly speaking, having a drift of magnetic fluctuations that goes at the Alfvén speed kind of makes sense, but it's not something that was predicted from theory. There's no reason that you should have this overshoot a priori, but we do see it in simulations, and we've tested it to see that it does occur at the local Alfvén speed for a bunch of different shocks. And so this is interesting because keep in mind that the cosmic rays are scattering off of these magnetic fluctuations. This is a collisionless shock. They're not actually interacting directly with the plasma. And so what that means is the cosmic ray frame is also going to drift. And so you now have a drift or a post-cursor of both fluctuations in the magnetic field as well as the cosmic rays. That's going to enhance escape from the acceleration region, which raises your fluid compression ratio, but also steepens your spectrum. If you want to be a little bit more quantitative about this, you can think of the post-cursor as modifying the compression ratio that particles see. So particles are no longer sensitive to this fluid compression ratio, U1 over U2. but this effective compression ratio, which is U1 over U2 plus VA2. Yeah.
What is the kind of ideal nature of the plasma that we're dealing with here? So when you say that the field is drifting with respect to background flow, is it quite a resistive kind of regime we're in, or?
Yeah, so it's the fluctuations that you amplify. So naively, you would expect those fluctuations.
What's the actual wave speed of these
The
fluctuations?
actual wave speed, yeah, so these are waves.
Right,
These are
right.
waves, yeah. Alphane-ish, but they're
I see.
kind of weird structures, yeah.
Thanks.
So the fact that you are creating, I guess, these magnetic field fluctuations, does it mean that the shock is much less efficient at accelerating particles because it's using a lot of the energy to create these fluctuations?
Yes.
That's a negligible.
The amount of energy, so if you put 10% of your energy or pressure into cosmic rays, the amount that goes into magnetic fields may be 5%. So you still have a lot of energy available to you. It's not a huge so it doesn't actually change it changes the cosmic ray spectrum in this way, but it doesn't actually, tap a ton of energy from your cosmic rays. It's tapping, in the end, it ends up all tapping from the shock. And it's a smallish fraction. Yeah.
Doesn't the geometry of the field come into play here, because the component of the field parallel to the shock normal is not being amplified, so that component of the Alphane speed wouldn't change.
So
The transverse component gets amplified.
so
Compression, but not
by compression, yes. But the fluctuations, those are isotropic when they're created. So it's true that you do preferentially, you don't amplify all components in terms of the compression, but the compression is actually a small factor. Most of the field is coming from the amplification that's happening up here. And that creates a tangled mess that's
so
roughly
just
isotropic.
some sort of turbulent application.
Yeah, this is the balance stability. So that, but you could play this game with some sort of turbulent amplification as well, but Bell is what we seem to see in simulations, and it creates this really strong weighted field amplification. Yeah.
So what's the approximation in the theory that makes it so you don't see the fluctuations?
So this is so you don't see the fluctuation
You said that this is some empirical observation that you see.
in simulations.
Right, yeah.
Yes.
So
Why don't you see it in actual observations of this?
no, I maybe I misunderstood. I thought you said that when people do the theory for this, like pen and paper theory,
Yes,
they don't predict.
They don't predict this, no.
What's the approximation that's in the theory that makes it so you don't?
So the approximation in the theory, you say that, if you're doing pen and paper theory, you just say that your magnetic fluctuations are frozen in with the plasma and everything is drifting together, and you don't allow them to move separately.
So why are the magnetic fields not drifting with respect to the plasma? What's actually happening in the shock that's causing this sort of decoupling of?
We're not sure. That's the kind of empirical result we weren't expecting. You do expect to have a drift in the upstream. That makes a little bit more sense. So you also actually expect to drift this way, so away from the shock in the upstream, and that comes from the fact that if you have escaping particles, they'll bring the magnetic fluctuations with them. And it's basically the nature of the way that you're driving Bell, but this was not something that we have a nice theory for why this should be. It's kind of a mysterious result, and it was only seen more recently because of these hybrid simulations just basically let us go longer. So we have to wait for this to show up. Yeah.
Sorry, I guess maybe I still don't understand why you would assume that they would move with the plasma itself. Because if you poke a magnetic field, which this is what you're doing, then you would expect it to move with the Alphane. So
no, and you could make some kind of cute arguments about this shock is a disruption, and it kind of acts as a little antenna, and so you're getting so you can make cute arguments about that. So that is maybe the reason, but there's certainly not the theoretical framework to do this, and so people will just say it's going at the plasma velocity. The other thing is, if you don't account for magnetic field amplification, this is actually quite small. So it doesn't really matter. But if you account for, that's actually my next point, strong magnetic field amplification, this VA2 can be a sizable fraction of U2. And so that can lead to a substantial effect. So the idea here is now you can actually get a fluid compression ratio, so R, that is larger than 4. but an effective compression ratio R tilde that is less than 4. And so if you want to put this in a more theoretical term context, this is kind of the new theory for what this is QP, so the momentum slope should be. And so now, instead of just depending, before it was 3r over r minus 1, you also have this alpha term, which depends on the alphane speed and the fluid velocity. Or you can actually recast all of this in terms of this psi v2, which is just the magnetic pressure fraction in the downstream. So if you are able to somehow, make a guess for what psi v2 should be, and you also guess what your cosmic ray acceleration efficiency should be, so that's basically the pressure fraction of the cosmic rays, then you can solve your hydro equations across the shock, including those pressures, and get a prediction for your fluid compression ratio R. And that in turn gives you a prediction for what the slope of your spectrum should be. And so that's basically what we do on this next slide. So this is the magnetic pressure fraction, this is the cosmic ray pressure fraction, and then this is in the color, the prediction for the slope that you should get based on when we solve for R. And so what you can see, if you believe that you have a 10% acceleration efficiency, you'll typically get spectra that are quite a bit steeper than e to the minus 2, somewhere in the 2.2, 2.4, or even higher, depending on what you do with your magnetic pressure fraction. But what I'll also mention is that magnetic pressure fraction is not a free parameter. And in fact, what I said about magnetic field amplification is that there is a relationship between psi v2 and psi cosmic ray. And if we say enforce the saturation point of the bell instability, it looks something like this. So this is assuming saturation of the bell instability. That saturation point does scale with the shock velocity because that dictates how much current you have available. But the idea here now is if we say, well, simulations tell us that we should have about a 10% acceleration efficiency based on how particles are injected. And if we say we have a 2,000 kilometer per second shock, then we can just read off that we should have a Q in the 2.2 to 2.4 range. So that's kind of this new predictive framework that we have developed. However, we want to be a little bit more self-consistent. So right there, when I played that game, I assumed a fixed cosmic ray acceleration efficiency. That's not necessarily true. We have a very nonlinear system here. And in particular, Q, the slope depends on the alphane speed. The alphane speed depends on cosmic ray-driven magnetic field amplification, and the cosmic ray pressure depends on its own slope. So you have to take this all into account self-consistently in order to make a prediction for the spectrum and something that you can actually reliably compare to observations. And so the basic idea to do this in a semi-analytic form is you want to solve the transport equation for the non-thermal particles crossing the shock. So this is taking, kind of the results that we have in particle and stellar hybrid simulations and reducing it to a 1D transport equation across the shock. This is a diffusion advection equation where you say some fraction of the particles crossing the shock are injected into this DSA process, and then you let everything proceed.
This is steady state.
Yes.
Is that okay?
Yes. So the timescales for this acceleration are much, much shorter than the evolutionary timescale of superconductor, which is what you care about. Minutes. So the idea here is if you want to include the post cursor, you are also considering not the fluid velocity, but this thing I'm calling U tilde, which is basically the velocity of magnetic scattering centers. So it has an alphane speed baked in, all of what I just showed with the post cursor. And so I will mention that this is actually not a closed system of equations on its own. You need a fluid velocity. You need to know what your diffusion coefficient is. This is something that's, we're going to assume bomb diffusion, but it depends on your magnetic field. And then, of course, you want to solve for your particle distribution at that speed. And so you need a system of equations that we basically solve iteratively. And so what we do is you start with a guess for what the solution to that transport equation should be. So that's basically a cosmic ray pressure when you integrate it. Then you put that into a prescription for magnetic field amplification. That will give you a magnetic pressure that you can combine with your cosmic ray pressure. Put all of that into your hydro equations, so just your jump conditions across the shock. That is going to give you a fluid velocity, which you can put back into your Parker transport equation. That will give you a new solution for what your cosmic ray pressure should be. And you basically do this iteratively until you converge on a solution for your particle distribution. And this gives you a prediction for what your proton distribution should be at any stage of the shock's evolution. You can take that instantaneous proton spectrum, use it to estimate the instantaneous electron spectrum. So this DSA only depends on rigidity. So in principle, your electron spectrum should be the same thing, modulo some normalization factor. And then you can also take those instantaneous spectra, weight them to account for energy losses, adiabatic and or synchrotron, if you're dealing with electrons. And then you can predict the cumulative particle spectrum you should get at any stage in the shock's evolution. Before I show you what that looks like, I just want to take a moment to mention what we're doing for this magnetic field amplification. Getting the field right is, of course, critical to getting the post cursor right. And so what we basically say is that in fast shocks characteristic of supernova remnants, the balancability is your dominant instability. It'll give you the strongest magnetic field by far. And so we take that saturation point here. This is predicted by theory. It's basically that equipartition argument I mentioned before. But what I'll also mention is it gives you fields that are consistent with real observations. So if you ask, what is the actual magnetic field and or Alfvén speed inferred from a real supernova remnant? As a function of we actually did it as a function of shock velocity, we get this scaling right. And we get the normalization right as well. So there's promising evidence that it's either Bell or something that looks very similar to Bell.
How are you calculating the diffusion coefficient?
So that we assume Baum diffusion, and once we have that magnetic field that comes from this, that goes into the Baum diffusion coefficient. So, in this environment where you have these large fluctuations, you expect to have the Larmor radius comparable to your mean free path, so you can assume Baum. If you wanted to have fun with it, you can put a factor on it and see how it changes things. But all right. So the other thing that I'll mention that's really interesting about this is it's actually giving us a predictive result that's comparable to observations. So if you believe that this is how magnetic field amplification proceeds, you can see that a faster shock should have a stronger magnetic field. A stronger magnetic field is going to give you a faster post cursor because you have a higher Alfvén speed, and that's going to give you a steeper spectrum. So we have this prediction that says that fast shocks should give you steeper spectra. It's an interesting thing we can take into account. So first, let's make sure that we get something that works for kind of a regular run-of-the-mill supernova remnant. So this is a Tycho-like supernova remnant. This is a well-behaved type 1a expanding into a relatively uniform medium, and it's pretty spherical looking. And what we find is if we include the post cursor, you go from an e⁻²⁵ spectrum, with that slight concavity, to something that goes as e⁻².3, 2.4, which happens to be exactly what you have inferred from the real Tycho supernova remnant. So it seems like we're right on the money here. We can then take this step further and do kind of a parameter sweep. So here I went through and did a bunch of different toy model supernova remnants, in this case expanding into uniform media, but I varied the density just to see what would happen. And you can see that the slope we get out, so the different models are shown in these lines. The shock age is shown on the x-axis, and you can see that there's relatively good agreement with the real slopes inferred from actual supernova remnants. This is from their gamma ray emission.
So what happened in the lower region where it doesn't go beyond into the 3? This is just
Yeah, so it's just that once you start to get too slow, like why there aren't observations of this?
no, I mean your theory, right? This line,
Yeah.
dash line, in the lower region, this dash line don't extend beyond into the 3.
So
And you have data points there, like down Q2.2.
Yes.
What's going on?
yeah, so this is basically where I ended the evolution. So this one is basically, let's see, so this one is a very slow supernova remnant. And so it basically the slow supernova remnant, yeah. I want to make sure I remember which one this is. So this particular one never actually so I should also mention this bend here on all of these guys is because when you start to slow down too much, the balancability is no longer dominant. And so you transition to the resonant instability. This one didn't run past 1,000 years, actually, sorry, because this is the really high density one. So because it was in such a high density, it became radiated really quickly. And I didn't want to model too far into the radiative phase because the evolution that I was using wasn't particularly reliable for it.
I see. So these 3 points which are not covered by the line, not necessarily a problem because you're
Yeah, so I would expect
You're
I need to do better modeling in the radiative phase here. And the other thing that I would mention, if you adjust, like this is a little bit tunable, depending on your acceleration of these assumptions about how you inject particles and stuff like that. So that this is not a perfect, this is the only way it could be. There's a little bit more of a spread on here. But what I can tell you is I can very comfortably make E⁻² spectra for something that goes as like a few thousand kilometers per second. In fact, I have that with novae. I did a project with that, and it's a little later in this talk. It's just that this particular one that I ran that went and met up here, happened to die at like 1,000 years because this was a really crazy high density in which to be expanding.
Are these all type 1A remnants or
These ones are, yes.
does it matter if you?
Yeah, it does. You can, if you want to make an approximation, you can say, well, let's ask what the density is now that the shock is encountering, and that gives you an approximation, but that approximation is actually a lot better for for type 1A supernova remnants, because you basically are more dominated by your last shell. If you are expanding into a 1/r² profile, you do need to take into account the full evolution of the remnant. And that's actually something we did. So the next thing we tested was not just, these are all galactic supernova remnants, but we wanted to see if we could reproduce radio supernovae as well.
The number density is not constrained, like you have such a big spread there. Like
the number density of,
like in the color bar, you have such a big spread.
yes. Yeah, so there are some math now. You'll notice that I didn't actually run one that was 10⁶. The idea was to kind of span the range of either, you have a supernova remnant that hits a molecular cloud or something crazy, or you have a type 1A that's in a relatively low density, medium far away from the disk or something like that. So that's why you have a huge range in densities. You're not crazy sensitive to your density. You still get, so you always have this trend with velocity. So inversely with shock gauge is the other way to put it. But no, it's true that if you change the density, it changes your result a little bit. It is reasonable to assume crazy ranges of densities, especially when you start to get into the core collapse, which is going to be the next thing. Because you have this wind that, it's very, very low density at large radii, but you expect to have even higher than 10⁶ particles per cubic centimeter close in when the shock is young.
So this object, you actually know which, what kind of density environment they are, right? So can you actually do this check to see if it works?
Yes, the uncertainties on the ambient density for these are large. And in many cases, you have to do some sort of filling factor average due to the fact that you might be encountering a denser medium on one side than the other. Hence the whole, what if you hit a molecular cloud or something like that?
But other magnitude, right? Because here even other magnitude measures.
Yeah.
You do a check that other magnitude, do they make sense? That compare your.
Yeah, so order of magnitude, again, that's why we did it with we did Tycho, which we know is about 1 particle per cubic centimeter with big error bars. It also works for Kepler. Some of these in here aren't even, so this is a model of a type 1A, not all of these are type 1As. So it's worth it. So if we wanted to do it properly, and I've done this for individual objects, you have to do the full evolution in the right environment. Especially the core collapse are tricky because you are likely going to see emission from when the shock was younger and probing a higher density. But the density it's probing now is a lot lower. So I played this game with individual objects. I'll show it with novae with AGN winds, but no, I did not go through each of these. I just did it for Tycho and I think Kepler, because I know it's also.
Or even kind of color code them with density tests.
Yes.
Upper one and lower one.
Yeah, I would say the uncertainties are very large. That's what I would say. And not all of them have a reliable density, so like ambient density associated with them. All right. So the bigger tests that I wanted to have was not necessarily can we just explain the range of 2.2 to 2.6 Q that you get with galactic supernova remnants, but what about these extragalactic radio supernovae? So what I'm showing you on this plot, this is alpha, which is the slope of the synchrotron spectrum, but it can be directly mapped onto the slope of a particle spectrum. So Q = 2 corresponds to alpha of 0.5, and alpha of 1 gives you a Q of 3. And so you can see that the galactic supernova remnants, so these kind of famous historical ones, all sit in this modestly steep regime. But when you go up and look at radio supernovae, which have these triangles, they're very steep. So they're more like e⁻3, with some variation. And so the question is, why are these ones so steep? And we said that we have this prediction that faster shocks should have steeper spectra. And these are all much faster shocks and they're a lot younger, which is why they are moving so quickly. And so I ran, a very simple toy model radio supernova. So I basically said that you have a young fast remnant expanding into a wind profile. What spectrum do I get after, say, a few years, maybe only 100 days? And in fact, you get something that's right here. So it happens to sit right on that Q = 3, which is circumstantial evidence, I would say, in favor of this model. The one other thing that I will mention before I move on to some comparison with observations in terms of, modeling specific systems and trying to understand those systems, is that this game does become a little more complicated when we're talking about electrons. So mostly I've been talking about this in the context of protons or electrons at relatively low energy, which is what's giving you that radio synchrotron. But cosmic ray electrons experience losses in these amplified fields. So if you have a field of 300 microgauss, and you have a 10 GeV electron, it's going to lose its energy on a time scale of roughly 7,000 years, which is much shorter than the time scale of a supernova remnant. And so this means that if you care about things like understanding cosmic ray leptons, you have to take this into account. The fact that, so this is the slope of the electron spectrum minus the slope of the proton spectrum. The electrons are going to be injected with a steeper slope, depending on your magnetic field. If you believe something like Tycho, it's going to be 0.2 to 0.4, depending. And so that's just another small project to keep in your mind. This matters for things like if you care about the positron excess, which might be evidence for dark matter. I don't think it is, but you have to take into account the fact that electrons and protons are not injected in the same way, which is commonly looked over in the literature. Yeah.
Do you care about anisotropies and the distribution functions of the particles?
When you say like anisotropies, spatial anisotropies?
In angle with respect to the magnetic field, for example.
Yeah, so we basically say when the field is amplified, so the distribution should be isotropic. Like most of, so the, like everything that I was doing for FXP is for the isotropic part of the distribution function, which is by far the dominant one. And then that first order correction is the diffusive component.
But the diffusive, bone diffusion is it's a scalar coefficient. So.
Yes, but there's basically an anisotropic component. Basically, there's a drift of particles that goes upstream.
But do you have a pressure anisotropy?
Yes, you do. So it's higher pressure, like in cosmic rays.
And that's just modeled in. That's modeled by the diffusion.
Yeah, so it's accounted for by the fact that you basically have a population of particles that's accelerated at the shock and then it's diffusing outward in the upstream. So yeah.
I have a nice question, like the supernova remnant that we were showing, like
Yeah.
a couple slides ago. So aren't there like multiple observations of remnants? Like in the beginning, you would have some, the shocks to be large velocities and then they fall. So you would have multiple data points there.
Yeah, so the thing is the time scale on which this change happens is hundreds to thousands of years. So are we talking, so you're saying looking at multiple supernova remnants of different ages?
A
single remnant, you're not going to see its velocity change enough for this to be detectable. What I showed you before. You might be able to see it with something like a nova, and I'll show actually applying this to a nova. It's very complicated because novae are a mess, and that was kind of the conclusion of that work.
Just a very quick question. So the magnetic field here is from 10 microgauss to 10 to the 4 microgauss.
Yes.
Does it correspond to what you actually may see in
This
the environment? This is a
gray
type
band.
of-
Gray band
Gray band is what you
is
actually
reasonable.
see.
Yeah. So we basically varied to see, we went crazy. You do see something like this for younger supernova remnants. So if you are talking about, if you ask what do you infer from a radio supernova, just with some naive assumptions about the synchrotron emission, you need like a Gauss field. It's really strong.
Why are the error bars so much larger?
Yeah, so this is error bars on the fact, it's basically the fact that when you seep in your spectrum due to synchrotron losses, it's actually a convolution of cutoffs. It's not a true power law, but it looks like a power law, and that's what people in the cosmic ray community use. So this uncertainty is actually uncertainty on the slope due to the fact that you have something that kind of is more of a rollover instead of a cutoff. So it's not a real theoretical uncertainty. It's just that people like to put things in power laws.
You said you need Gauss fields and young supernovae?
Yeah, so if you make an argument where you have like equipartition between the, which is not necessarily true, but if you go talk to the radio supernova community and you say you have equipartition between your electrons and your magnetic field, and then you have some synchrotron emission and you want to fit that normalization, you need like a Gauss field to do it.
How can you do it with the balance of stability going from micro Gauss to Gauss?
Yeah, so you have a much faster shock, so the saturation point is even higher. It does make it so it comes if you run it through, you do get the much stronger field. Also, some of that is likely the inherent field that was already there. So if you're dealing with a radio supernova, you're expanding to this dense wind. And so likely some of that is the fact that you've had a magnetic field that was very high, just simply due to the fact that it's a dense medium. And so the magnetic field likely will rise with that. But there are huge uncertainties on what that is. I can tell you that if I run something like a radio supernova, you do get strong enough magnetic field amplification that you get something pretty close to it.
Bivalent stability can do it. And I think if you need to amplify it by a factor of 1,000,000, bivalent stability is a better bet.
Yeah, it might be. So in those environments, I won't say that Bell is the be all and end all. As far as I'm aware, there are issues with Bell or with Weibel getting to the right scale of fluctuations to actually.
That's not the story, that's right.
Yeah.
It can dissipate quickly, but if you need to adjust the shock font, you can.
Yeah. Well, but no, I think, and some of it I think is probably just the ambient progress. So there's that as well. Great. So we made it to the second part of the talk, but I'm nearing the end of time. So I've teased that nova. So I'm just going to take a moment to mention the story of that nova and something we can learn. But I have lots of other projects that I'd be happy to talk about at some point during coffee or what have you. But the story of this nova, so okay, the transition point, cosmic rays interact with stuff that produces photons, as well as neutrinos in some cases. And so mostly I'll be talking about the radio gamma ray emission that we can observe from these cosmic rays and what they can tell us about shocks. In particular, I'm going to skip ultra-fast outflows. These are AGN winds, but we can fit spectrum. It's cool. Moving on to an example of kind of a miniature supernova remnant is a nova. So novae, the picture to have in your head is you have a white dwarf with in a binary with some sort of either main sequence star or red giant. I'll mostly be talking here about the idea of a symbiotic nova, which is where you have this red giant companion. They're interesting because if you have a red giant, you likely have a red giant wind. And so if you have some sort of outflow, it's going to expand into a much denser medium. That means you have a shock that's processing more mass, and you can produce more cosmic rays and also more gamma ray emission. Since the idea here is you actually both increase the number of bullets, you increase the number of cosmic rays, but you also increase the number of targets for proton-proton interactions, which is the way that protons can go on to produce observable emission, specifically gamma rays. And so this white dwarf is accreting material from the red giant, eventually ignites runaway fusion on its surface that launches an outflow, but unlike a type 1a supernova, it does not destroy the white dwarf. And so this one that I'll be talking about, Astrophysics, goes off once every 15 to 20 years. And so it went off for us in 2021, and we were all very excited about it because it was the first time that we got TeV emission from a nova. So normally we've seen gamma ray emission from these things before. It's in the GeV, which implies a pretty low energy cutoff. But here we actually have tera-electron volt emission, which basically means that for something the size of a nova, it's accelerating very close to its theoretical maximum energy. It's promising in terms of what we can learn about particle acceleration.
This was the first time because instruments just happen to be better now, or?
So yeah, it was a combination of, so like the last time that RSFUQ went off, there were no TeV telescopes to look. So, however, RSFUQ is also brighter. So it's a much, one, it's the symbiotic. A lot of classical novae, the ones with the main sequence companions, do produce emission, but it's likely from internal shocks. So basically outflows hitting other outflows. This is likely a forward shock because you have that dense wind to work with. So it's a favorable nova, but it's also a favorable time. That makes sense. Yeah. So if you look at, these are the light curves from Fermi, so GeV and Hess in the TeV. And the first kind of notable feature of this is that there is a clear delay with respect to the peaks. And the discovery paper said that this is because there's a finite acceleration time for TeV particles. And this might be that finite acceleration time that we're seeing, which would be very exciting if we wanted to learn something about particle acceleration. But I sat down and tried to calculate what we'd expect the finite acceleration time to be, and it's less than a day. So it should all happen back over here somewhere. And so there's a problem with this picture. And in fact, this is not the only problem. So I went and tried to apply this semi-analytic framework that I've developed to our Astrophysics, and what I got is bad. And so what you're seeing here is, so this is the light curve on the left, this is the spectrum on the right. So the blue and the red are Fermi and Hess respectively. And then here, these are two different epochs. So this is at 1 day and 5 days. And so what you can see is I can go ahead and fit the Fermi flux really well, but then I way overshoot the Hess flux. Or if I change my model parameters, I can conversely fit the Hess flux and way undershoot the Fermi, but I can't fit them both at the same time. And the reason for this is multifold. First of all, I cannot reproduce the delay, and that makes sense given the fact that the acceleration time is much shorter than the time it takes to get to this peak. And so once you're accelerating both GeV and TeV particles, it's the same shock that's producing all of this, the two spectra should evolve in lockstep. There's no reason that one should drop before the other. The second thing that you obviously have is that I'm way overshooting Hess. And the reason for that, you can think of it as the fact that this shape here over in the spectrum is not fit by a power law with an exponential cutoff. So you've got kind of a nice e⁻² spectrum here. So this is a case where I can produce something closer to e⁻². But then you have, this is maybe some sort of power law. Certainly this is never going to connect to this. And the other way to think about it is there's no way to have this thing, so this 1 day, go down. So you can't go down in the GeV while going up in the TeV, which is what you need to have happen here. So go from green to purple, you need to actually increase your flux. And that's never going to happen with one shock, one population of particles. I even played the game where I said, well, what if this is actually a multi-zone model. So what if it's that you have different zones that are contributing differently? This takes all of that into account, and it's not enough. It doesn't change the shape. The way that the discovery papers fit this is they put some sort of artificial slow rollover into the cutoff, which is invisible. And so this implies that you actually have the presence of multiple outflows. So I am relatively model agnostic, but I took the kind of naive expectation where you have a binary, so you should have some sort of disk. So there should be, what if you had some slow shock moving into a dense medium in the plane and a fast shock moving into a low density medium in the poles, and just played that game, messed around with my parameters a little bit because there's wild uncertainties on things like the density, so I can play some games. And what you get is something that can fit quite nicely. And so I think there's very clear evidence for the presence, not necessarily of this picture, there could be more shocks, but you cannot do this with a single external shock. And the point is that novae, which we love to think of as these nice little analogs for supernova remnants that evolve on a time scale of days to a month, are unfortunately more complicated, largely due to the fact that you have the presence of this binary and it's an intrinsically asymmetric system. All right, so I'm pretty much toward the end of time, so I'm happy to take questions, or if there is time, I can go through some of these cute projects. Cosmic rays can make supernova remnants live longer. The maximum energy is a problem because we can't always reach this need with supernova remnants. But I'll just finish for now by putting up my summary slide and say that we have a framework for how galactic cosmic rays are accelerated, and it can teach us things about galactic cosmic ray accelerators, including objects like novae, fast AGN winds, and also how cosmic rays, extend the lives of supernova remnants and other fun projects. Thank you very much.
I'm confused about this multi-shock here. So if you have a multi-shock And do you have to have the ratio between G and T to be very different from the shock to produce this pronounced delay?
Yes, so basically what's happening is you have two shocks that are evolving differently. They, start to, so going back, the peak here is set largely by the transition to the Stanhope-Taylor phase. So this thing is ejecta dominated and then it starts to slow down and it all happens very quickly because you're expanding into a very dense medium and you don't have a lot of ejecta mass to work with. And so you have basically two different shocks that can enter the Stanhope stage at two different times, depending on the profile of the ambient medium, which is something that I can play with. But the kind of reason for these this discrepancy in what they produce is that the slow shock is going into a much denser medium, so it's going to have a much higher luminosity because you're saying it going into something like a disk. But it's also much slower, which means it has a lower maximum energy. So that's why you see the slow shock is these dotted lines and it cuts off at lower energies. And then the fast shock, much lower density medium, so relatively rarefied. And so it's a much lower luminosity overall, but it reaches higher energies because it's fast.
So presumably you have these two different velocity, then in the nova remnant, would you see signature of these two?
So we see in optical line emission evidence for at least two velocity components, and they're at roughly these.
Roughly work?
Yes, yeah, give or take, because there's a third component that appears and disappears for a little bit, so I think there's some uncertainty there, and that's likely the fact that this probably isn't even just one outflow. There might be some collisions, some internal collisions on top of that that we're seeing evidence for, but this was trying to basically create the simplest possible model that would reproduce the data.
At what densities do collisional losses start to play a role? Does that need to be included?
Yeah, so proton losses are included here, because that can affect the cosmic rays. In this case, the loss time here is a fraction of a day, so it tempers the spectrum a little bit, but you're not calorimetric or anything like that.
But at what density does it sort of become fully collisional?
Yeah, I think you have to be I want to say 10 to the 8, 10 to the 9 particles per cubic centimeter, you're fully calorimetric.
For your shock acceleration model, is there any numerical evidence that actually shows that at a precursor there's an extra speed caused by the upstream magnetic field?
So,
because it's a highly nonlinear process.
So you're saying evidence for the precursor
that you have an extra VA or other velocity that is caused by the upstream magnetic field. Is it just
caused by the upstream? So that's predicted from theory, but so that one, even detecting the precursor at all in a shock is very difficult. And so there's been some shady evidence based on estimates of diffusion coefficients and so on. But detecting a drift of magnetic fluctuations on top of the precursor is not something that we have. And downstream, everything is a mass. So if you wanted to look for the postcursor, the length scale, I should clarify, the length of the precursor and the length of the postcursor, very microphysical relative to a supernova remnant. So resolving it is not going to happen. And the length scale on which you lose, or basically on which you damp out your magnetic field in the downstream, for example, is often much smaller than your resolution. So there's no direct way to observe this, unfortunately. Simulations are kind of the best we have.
I have one question. You said this multi-component model, for novae, but also for supernovae, there could be cocoons or something like that.
Yes, no, I've wondered with the really young supernovae, I think this could again be relevant, especially because there have been radio supernovae that have evidence for the formation of a disk of some sort, so not a binary situation, but still forming a disk when they explode. And I think you could absolutely play these same games. The nice thing about this kind of semi-analytic framework, it's 1D, but the shock is a 1D object. relative to the scale, like if you consider the, larval radius of these particles compared to the size of the system. So you can basically just run it in a lot of different directions and see what happens, with different profiles as you go. And that's actually something I want to work on here. But yes, I think it's very possible that supernova remnants, especially young ones that aren't very well behaved, need some sort of treatment like this.
Let's thank Rebecca again.